Hello and welcome. In this video, we're going to go over series power. Series power is associated with our voltage drops for series circuits. So we know that there's a voltage drop, VR1, and a power drop, P1. Right, and we also have a VR2 in P2, a VR3 in P3, and a VR4 in P4. Right, so we'll have a power drop and a voltage drop for each one of our resistors. There's also a concept called voltage to ground, and that would be if we were to attach a voltmeter across these two and we measured the voltage across those two locations, right? Or from node A or node B down to ground also. And we know that we can get those voltages specifically as well. Right? That's going to be called our voltage to ground. So keep in mind the difference between voltage to ground and voltage drop. Sometimes they're the same, sometimes they're not. So this one, we are going to focus on getting our voltage drops across each one of our resistors, and we're going to use that in our power equation. We know that power is equal to voltage times current. So P equals I times V. And specifically, if we want to know our power 1, we can say power 1 is equal to our total current, since this is a series circuit, multiplied by our VR1, voltage drop across that first resistor. So we need to find the voltage drop across the resistor, and we also need to find our total current. We know total current is equal to voltage over resistance. So we can say IT equals Vs, the voltage source, divided by our RT. We can solve for that. We just need to find out our RT first. So let's do that. So in our Desmos, we can find our RT by summing up all of our resistors. We keep in mind that the notation matters on this. So the kilo ohms that we see on all of those all match. So we can just add them up. 3.5 plus 2.4 plus 6.4 plus 1.2. That's going to give us 13.5 total resistance. 13.5 kilo ohms. And we can plug that in for our IT. That's our 27 volts divided by 13.5 K ohms. We can solve that out. Now we have to account for all of those zeros in this one. So 27 divided by 13,500, right? So I move that decimal point over by 3. So now we have a current. We have 0.002. We can move that over also, and we can get 2 milliamps. All right. So now we have our current. We can plug that in for our voltage drop. We need to find our voltage drop. So that's our voltage divider equation. Send this out. We'll set up our voltage divider. Our voltage divider says that we want our R1 on top. So we'll open a parenthesis. We'll put R1 on top, 3.5, divided by our total resistance. We know that, 13.5. And we will multiply that ratio by our voltage, 27. So now we have 7 volt drop across R1. Right, so now we know that one. So let's erase some of these, and we'll plug in some of these values we know into our circuit. So we know that we lost 7 volts across R1. That's our voltage drop, VR1. We want to find our power through that, so we can plug that into our total current equation here. Send this one out, and we'll say that we have our total current of 0.002. That's our small current, right? Our milliamp value in amp form. And we can multiply that, just like our power law says, by our voltage drop across that specific resistor R1, and that's 7. So now we know the power across that. We know that the power, PR1, across this first resistor is equal to 0.014. We'll move that over, and it'll be 14 milliwatts, right? It's power, so it's watts. We can do that for each one of these equations here. We can go for the voltage and the power drop across R2. We know that that's just swapping out our top of our equation here. So 2.4 on top of our voltage divider divided by our total resistance multiplied by our voltage source gives us 4.8 volts. And we can find our power using the equation right below that because our current stays the same. Now we know that we've got 4.8 volts here, which means that we have, we'll move that decimal point over by 3, 9.6 milliwatts. Right? And that is the power drop across R2. Let's keep going. Let's go for the next one. We can replace the top of our voltage divider equation with 6.4 kilo ohms divided by our total resistance multiplied by our source voltage gets us 12.8. And that's in volts, right? 12.8 volts. Then we'll go after our total resistance equation. We'll replace this 4.8 here with a 12.8 volt drop. We're given a little bit larger power there, so we'll move that over by 3, and we're given 25 0.6 milliwatts. That makes sense, right? Because this is the largest resistor in the circuit. It should have the largest voltage drop and the largest power drop. Let's keep going. We have one more here, so we can do our voltage drop across the bottom, 1.2. That gives us 2.4 volt drop across that bottom resistor, R4. So 2.4 volts. And we can find our power with our 2.4 volts being placed in for this equation here. So 2.4. And that gives us the smallest current that we've gotten so far. So we'll move that over, 1, 2, 3. We got 4.8 milliwatts. So this is verifiable. We can double check this by summing these together and proving our total power, because we know total power, PT, is equal to our IT multiplied by our voltage source. So let's do that. Let's double check this. So let's say that our IT is that 0.002 multiplied by our total voltage of 27 volts. So we expect our total power, PT, to equal, we'll move that decimal point over by 3, we get 54 milliwatts. Right? So that means that the sum of all of our power drops should equal this exact same value. So let's send this out. We'll say 14 milliwatts for the first one, plus 9.6 for the second one, plus 25.6 for the third, plus 4.8 for the last one there. We get exactly 54 milliwatts, right? So that confirms that we got the correct power drops. Okay, let us know if you have any questions.